Hey, and welcome to podcast 10.2. All I'm going to do here is explain vapor pressure to you, and we'll talk a little bit about types of molecules and how that changes the vapor pressure, the melting point, and the boiling point. All right, so this is just a pile of green liquid sitting there, and you're going to notice here in a minute, one of the liquid molecules turn into a gas. And as it turns into a gas, you're going to notice this gray stuff in the tube start to move. And that gray stuff is mercury. It's generating a vapor pressure because as the vapor gets created, and you're watching more and more molecules get created over time as the liquid evaporates, it's going to push on that mercury. And at some point, that rate of condensation will reach the rate of evaporation. Then you get to a place of dynamic equilibrium. What have we got? If we freeze time right now, we've got a bunch of vapor molecules, a little bit less liquid molecules, and that H in the middle, that is the height of the mercury difference, and that can give us some indication of pressure. How many molecules turn into a vapor affects vapor pressure. Pure and simple. The more molecules you have that escape to a vapor, then the more vapor pressure you're going to create. So let's just take a look at a molecule like methanol. Now, methanol is just this molecule. And methanol is pretty small, and it has an oxygen, and so it should be able to hydrogen bond. That would kind of make sense. So let's see what kind of vapor pressure we get. So all I'm going to do is I'm just going to take and create vapor pressure at different temperatures. So as you can see, as I increase the temperature, I'm getting a little bit more and a little bit more vapor pressure. So I'm going to pause for a minute, and I'll just fill in the rest of the graph. Okay, I'm back, and I'm all the way up to 89 degrees, and you'll notice that as I've increased the temperature, the vapor pressure goes up. And it happens because as there's more energy available to speed up the molecule, we measure that as temperature, there's more molecules that can leave the liquid phase and go to the vapor phase, right? So let's keep in mind that at 90 degrees, the vapor pressure of methanol is 1,821 millimeters of mercury. So just kind of write that down. Methanol is 1821 at 90 degrees. And then let's go pick a different gas real quick. Let's pick ethanol. Now, ethanol is this molecule right here. Ethanol is 1164 millimeters of mercury. And if I just draw the same graph, this time going down in temperature, you'll notice that the vapor pressure falls. And again, that's just because as temperature falls, there's less energy available for the liquid molecules to turn into a gas. Let's pick something like water. You know what water looks like. And let's take it back up to 90 degrees. 90 degrees, the vapor pressure is only 529.4 millimeters of mercury. Way less than ethanol. And why is that? Because it has more intermolecular forces. It has those hydrogen bonds that hold it very tightly to the other water molecules. And because of that, it's harder for them to turn into a vapor. So let's see if there's a molecule in our menu here that we can pick that doesn't have those hydrogen bonds. So let's go down and pick pentane. Well, pentane looks like this. Notice, no oxygens at all, just carbons and hydrogens. So that means that there's very little hydrogen bonding going on. In fact, none. All of the bonding here is going to be London dispersion forces. So let's see, what's the vapor pressure at 90 degrees? It's 3,542 millimeters of mercury. And if we crank the temperature down, notice it's not even showing up on the graph until I get way down here. And notice how steep a graph it is too. That's because it's easier for those molecules to turn into a vapor. Let's pick hexane. Hexane is a little bit bigger molecule. Hexane looks like this. All right, so one more carbon, still no hydrogen bonds, only London dispersion forces. So let's take a look. I'm going to crank it back up to 90 degrees. Let's see what happens. Now notice something about the graph. You'll notice the graph is not going up quite as steep as it was before. Are we going to get to 3,500? Nope. 1,423. Why is that? Well, it has more London dispersion forces because it's a bigger molecule. It has 6 carbons, not 5. Now, realize that once you have this down, the idea that vapor pressure has to do with what kinds of intermolecular forces, then that helps you with melting point and boiling point. All right, so just to show you what happened in 2013, what do they care about, right? They want you to understand hydrogen bonds, London dispersion forces, how that affects vapor pressure, and thus how it affects boiling point. So just looking at these molecules, carbon tetrachloride and dichloromethane, if you look at it, the boiling point is much lower in the dichloromethane, and also notice that it has a much higher vapor pressure. Now remember, vapor pressure affects boiling point because when you can get the vapor pressure equal to the outside pressure, so the pressure around you, that's when it boils. So at a very low temperature, it can generate enough vapor pressure to actually boil. So dichloromethane must not have very many intermolecular forces because it can turn into a gas crazy easy. Carbon tetrachloride, on the other hand, has a fairly low boiling point, but not as low as the other one. And its vapor pressure, if you notice, is also quite a bit lower. What does that mean? Well, that means the molecules have greater intermolecular forces. They have more London dispersion forces in them. Well, why is that, do you think? Well, you can do the math. Add up dichloromethane, 1 carbon, 2 chlorines, and 2 hydrogens, and then add up a carbon and 4 chlorines. Who's bigger? Who has more electrons? And the more electrons you have, the more London dispersion forces you have. So this is just one example of how AP is going to expect you to know this. Difference in your vapor pressure is governed by those intermolecular forces, and that affects boiling point. All right? We'll work on this some in class, and for now, I think that'll do it. See you later.